Now let's do hypothesis tests for population proportion. Step 1 is writing H0 and H1, the null hypothesis and the alternative hypothesis. The example says the voter turnout, the percentage of registered voters who actually vote, is lower than last election's turnout of 63%. So that means the alternative hypothesis that the population proportion was less than 63% or 0.63. And so then for our null hypothesis, it means that P is equal to 0.63. Now, next would be the critical values and rejection regions. The critical value is the z-score that corresponds to alpha probability to alpha probability in the tail. Or tails, if we have a two-tailed situation. Okay, the rejection region. So the rejection region is a range of values for which the sample data is convincing enough to reject the null hypothesis. This is the key observation. So we'll be working on establishing the rejection region. So we have strong evidence to reject the null hypothesis if the sample proportion is too many standard deviations. Is too many standard deviations from the proportion stated So if the sample proportion is too many standard deviations from the properties stated in the null hypothesis, then we reject then we reject the null hypothesis. So this sets up the conditions for rejecting the null hypothesis. This is key. So for a right-tailed test, okay, the rejection region can be right-tailed, left-tailed, or two-tailed according to the direction of H1, the alternative hypothesis, in the hypothesis test. So for a right-tailed test, this area is alpha. So that's the probability in the right tail, this little region here. The value here along the horizontal axis is z sub alpha, and that is the so-called critical value. Critical value. Similarly, for a left-tailed distribution, this area here is alpha. This is z sub alpha, and that's also, again, the critical value. Now, for a two-tailed test, alpha is split in half. So alpha divided by 2 is in each critical region. So there's alpha divided by 2. So together they represent alpha, this region plus that region. And so this would be z sub alpha divided by 2. And this is minus z sub alpha divided by 2. So here we have the two critical regions for a two-tailed test. Here we have a critical region on the left, and here we have a critical region on the right. The next step is finding the critical value. So here's our distribution, and we have a left-tailed test with alpha equal to 0.1. So that means this area here is equal to 0.1. So we look at our z-score table and look for the area, the z-score that corresponds to the area of 0.1, and we find that to be minus 1.282, or you can also use, of course, technology if you prefer that. So either way, that is our critical value for this left-tailed test with alpha being 0.1. Now, when we have a right-tailed test, we look for the critical value for alpha equals 0.05. So again, the area here is equal to 0.05. The area is equal to 0.05. And so we look up the z-score for the area corresponding to 0.05. And well, we can do it in one of two ways. We look up the value, the z-score for 0.05, and since we know that's a negative value, we make that a positive one. Or we look up the value for, or we look up the value for 1, since the whole region is 1, and this is 0.05. So 1 minus 0.05, which is 0.95. So the z-score corresponding to 0.95 is 1.645. So this is our critical value, z sub 0.05 equals 1.645, and this was our critical value minus z equals, or z equals minus 1.282. Okay? So that's how we look up the z-scores for a particular alpha value. It's the same thing we have done in previous chapters. When we have a two-tailed test and we are asked to find the critical values for alpha equals 0.01, then that means that each area has 0.005 as probability, 0.005. So this now would be z sub 0.005, and this would be minus z sub 0.005. And so when we look up the values, we find that is equal to plus or minus 2.576. Obviously it's symmetric about the center, and so we look up, let's say, the area for the z-score corresponding to the area of 0.005, and so we find that's equal to minus 2.576. Then, therefore, on the other side, it's going to be plus 2.576. The next step is to compute the test statistic. Now, provided that the necessary requirements are satisfied, the sampling distribution of p hat is approximately normal, with a mean of mu sub p hat equal to p, and with a standard deviation sigma sub p hat equal to the square root of p times q divided by n. So for a hypothesis test about a population proportion, The test statistic is a z-score. It's called a proportion test. And z is equal to p hat minus p sub 0 divided by the square root of p sub 0 q sub 0 divided by n, where q sub 0 is equal to 1 minus p sub 0. And p sub 0 is the value from the null hypothesis. Okay, so remember that it's not from the sample proportion, p hat. So in other words, this is the value stated in the null hypothesis. And then there would be the corresponding value for q. And here's the requirements. When the sample is obtained from random sampling, and if n is less than 5% of the population, n being the population. And so in other words, we can treat the observations as independent binomial trials. And when the mean n times p is greater or equal to 5 and n times q is greater than or equal to 5, so we can use the normal approximation to the binomial. So let's look at an example. In a 3M privacy filters poll, 806 adults were asked to identify their favorite seat when they fly, and 492 of them chose a window seat. Use a 0.01 level of significance to test the claim that the majority of adults prefer window seats when they fly. So what does majority mean? More than 50%. So in other words, here it's easier to start with the alternative hypothesis, H1. So that means P is greater than 0.50. That is the majority. So this tells us that the null hypothesis is P equals 0.50. So let's write down what we have here in terms of critical value and the rejection region. So we need to find the z sub 01 value for a right-tailed test. So let's draw out the distribution and the rejection region. So here's our distribution, and here's z sub 0.01, and here's our rejection region. And when we look up the area 0.99, we find that the corresponding z-score, z, would be 2.326. In other words, that would be the area to the left, would be 2.336, but that is our z-score for the critical region. So, next we need to compute our test statistic. So using the formula for the test statistic, z equals p hat minus p sub 0 divided by the square root p sub 0 q sub 0 divided by n, we then get 492 divided by 806 minus 0.5 divided by 0.5 times 0.5 divided by 806, and that z-score happens to be 6.27. Now let's think about what that implies. That means the z-score for the test statistic is more than 6 standard deviations to the right. Step 5 is making a decision. There are only two possible decisions. We either reject the null hypothesis, reject H0, or fail to reject, fail to reject the null hypothesis. So we use the rejection regions to make our decision. So we reject the null hypothesis if the computed test statistic, the z-value we just computed, is far enough out into the tail to be in the critical values rejection region. Otherwise, we fail to reject H0. So again, if the computed z-test statistic is far enough in the tail to be in the critical values rejection region, then we reject the null hypothesis. Otherwise, in other words, if not, then we fail to reject the null hypothesis, H0. So let's go back to our example. So the null hypothesis was p equals 0.5. The alternative hypothesis p is greater than 0.5. We found the critical value for the alpha equals 0.01. It's a right tail test. And we found the critical value was 2.326. That's our critical value. And the rejection region extends to the right. And we computed our test statistic as z equals 6.268. That's our test statistic here. So if our z-score, that means our test statistic, so that refers to the test statistic, is that above 2.326? Well, 6.268 is certainly greater than 2.326. So therefore, therefore we do reject the null hypothesis. So if our test statistic z-score is not above 2.326, we fail to reject the null hypothesis. So the decision is reject the null hypothesis or do not reject the null hypothesis. In this case, we reject our null hypothesis because 6.268 is certainly greater than 2.326. In other words, more than 6 standard deviations above the mean. So here, yes, reject the null hypothesis. So here's how we write our conclusion. We begin with, at the, in this case, 1% level of significance. This data does provide significant evidence to conclude that the majority of adults prefer window seats when they fly. So in this case, we rejected the null hypothesis, and again, we stated at the 1% level of significance. This data does provide significant evidence to conclude that the majority of adults prefer window seats when they fly. And obviously, we do not fail, or we do not reject the null hypothesis. That is not applicable here. In this example, we had a preset conclusion, how to write it. Down below here is another way, or it's a space to write your conclusion, but it would pretty much follow the example we used above here. So I'm not going to rewrite that again here, because it'll be the same thing. At the 1% level of significance, this data does provide significant evidence to conclude that the majority of adults prefer window seats when they fly. It'll be the same sentence we had up here. The next example deals with why you love text messages. A recent report from the Princeton Survey Research Associates claims texting by adult cell phone users is up compared to the 70% reported in September 2010. They sampled 2,252 adult cell phone users and found that 1,581 said they sent and received text messages regularly. Use a 0.05 or 5% significance level to test the claim. Well, the first thing is you want to make sure that the requirements are satisfied to even perform a hypothesis test. And so we know it's a simple random sample. And the sample size is certainly less than 5% of the population size, so the assumption of independence is satisfied. Then when we consider that P0 is 70% or 0.7, then n times the sample size is certainly greater than 5, and then n times 1 minus the samples, n times minus 0.7 is also greater than 5. So all the requirements are satisfied, and we can use the normal to approximate the binomial. So step 1 would be to write our hypothesis, and again the the null hypothesis is P equals 0.70, and the alternative hypothesis is P greater than 0.70. So in other words, we have a right-tail test here. Step 2, we need to compute the step 1 hypothesis. Hypotheses. In step 2, critical value. Critical value and rejection region. So you always want to draw a little picture to visualize what you're supposed to do. So we graph our distribution, and here's our rejection region, which is 0.05, and so the corresponding z-score is 0.212, whether you use technology or use the z-score tables. Step 3 is to compute our test statistic. So when we compute our test statistic, this is p hat, the sample proportion, minus p naught, divided by the square root of p naught times q naught, divided by n. That is equal to 0.2115, or we can round it up to 0.212. Of course, you can also use technology and save yourself a lot of computation. So if you're equipped for that, that's great, no problem. I just want to show you how you can do it without using technology. The next step is, step 5 is to decide. And what are we deciding? We're deciding if the test statistic 0.212 is in the rejection region. Now remember, the rejection region begins at 1.645, so 0.212 is about here. So in other words, the test statistic is not in the rejection region. The test statistic 0.212 is not in the rejection region. Is not in the rejection region. And this is why we always recommend to make a graph, so that you know what you're doing. So that means we would fail to reject the null hypothesis. Step 6 would be the conclusion. The conclusion is simply this: that at the 5% level of significance, the data does not provide significant evidence to conclude the texting by adult cell phone users is up from the 70% reported in the year 2010. So that is the conclusion. So here's the statement again. At the 5% level of significance, the data does not provide significant evidence to conclude that texting by adult cell phone users is up from the 70% reported in the year 2010. Here's another way to ask if we can use to decide if there's sufficient evidence to conclude the alternative hypothesis. So it begins with the assumption that the population mean is where it is, where the null hypothesis says it is. How unlikely would it be to obtain a sample like the one that we got? And when the data is too unusual, or the data outcome is too unusual, we take this as evidence to reject the null hypothesis. So this has to do with the p-value. So what is the p-value? Well, the p-value is the probability of getting a sample with a z-score as extreme or more as a result we got from the current sample. In other words, how rare is this data? And so then the p-value is computed as the area in the tails beyond the computed test statistic. So in other words, we're referring back to the test statistic. So here gives the definition. So the p-value is computed as the area in the tails beyond the computed test statistic. In other words, it's a probability. That's what the p-value is. Keep that in mind. By the way, it does not refer to the population proportion or anything like that. So it's actually a capital P. It should always be written with a capital P, so that we don't confuse it with the population proportion. So when we have a left tail test, the p-value is computed as the area to the left of the computed z-score. In other words, if this is our critical value, z sub alpha, or minus z sub alpha, then do we have the p-value would be to the left of the computed test statistic. Okay, so it says computed z-score, it really means the test statistic. Similarly, for a right tail test, the p-value is the area to the right of the computed z-score. So again, the p-value is computed for a left tail test as the area to the left of the computed z-score or test statistic, and for a right tail test, it's the area to the right of the computed z-score or test statistic. Now for a two-tailed test, the p-value is twice the area. Twice the area. Twice the area. So for a two-tailed test, the p-value is twice the area in whichever tail applies. Let's talk about the p-value and how it relates to the rare event rule. These statistical significance measures whether the result observed in the sample is unusual under the condition that the null hypothesis is true. And so here's the rare event rule. When this type of rare event is observed in the data, rather than continuing to assume the null hypothesis is true, the more likely conclusion is that the assumption in the null hypothesis is probably false. So the p-value does two things. It tells us how rare is this event, and a rare event tells us to reject the null hypothesis. There are two advantages of p-value approach versus the classical approach. One advantage of using p-values over the classical approach, that means computing the test statistic, in hypothesis testing, is that p-values provide information regarding the strength of the evidence. Again, the first advantage is of using p-values over the classical approach in hypothesis testing is that p-values provide information regarding the strength of the evidence. And the second reason is that p-values are interpreted the same way regardless of the type of hypothesis test being performed. The lower the p-value, the stronger the evidence is against the null hypothesis. So again, the second reason is the lower the p-value, the stronger the evidence against the null hypothesis. So how strong is the evidence? If the p-value is less than 0.1 or 10%, some evidence of H1, the alternative hypothesis. P-value less than 5% or 0.05, significant evidence of the alternative hypothesis. P-value less than 1% rather, very strong evidence of the alternative hypothesis. So you may want to remember these, how the strength is measured. So here, in step 5, making a decision using the p-value, what we're doing here is we compare the p-value to the significance level alpha. So if the p-value is less than alpha, if p-value is less than alpha, we reject the null hypothesis. Otherwise, fail to reject the null hypothesis. In other words, if the p-value is not less than alpha, do not reject the null hypothesis or fail to reject. So when we look at the previous example, our test statistic z was 0.212, and our p-value is, p is the probability that z is greater than 0.212, and that's equal to 0.4162, whether you use technology or use the tables. And so the question is, since alpha was 0.05, the significance level was 0.05, so the question is the p-value less than alpha? Well, the p-value is 0.4162, and alpha is 0.05, and that's clearly a no. And therefore we fail to reject the null hypothesis. The p-value is not less than alpha. So we do not reject the null hypothesis. Let's end the section by looking at one more example. Trust the media. In 2007, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In 2012, of 1,010 adults nationwide, 525 stated they did not trust the media. At the point alpha equals 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has changed since 2007? So, step 1 would be to write our hypotheses. So our null hypothesis would be p equals 0.46, and it says here that they do not trust the media, so that means the alternative hypothesis P is not equal to 0.46. So we have a two-tailed hypothesis test. So now we need to look up, draw a sketch in the rejection region. And since it's a two-tailed test, there are two rejection regions. So here are our rejection regions, each with an area of 0.025 on the left and the right. And the corresponding z-score, the z-critical value, is minus 1.96 and plus 1.96. So now step 3 would be to compute our test statistic. So our z-score, when we use technology, the test statistic z-score turns out to be 3.813. So that's our test statistic z-score. Now, the p-value, since we'll be using this now in this example, in other words, the two times the probability that z is greater than 3.813 is equal to 0.000137. Again, you can use tables for that, or you can do it with technology. Either way, this is our p-value. And step number 5 is where we decide. We're going to do it in two ways. Number 1, we can ask, is z, our test statistic of 3.813 in the rejection region? Well, the critical value is 1.96, so 3.813 is in the rejection region. Is that in the rejection region? Yes. So reject the null hypothesis. The other way to confirm it is to ask the question, is the p-value less than alpha? The p-value is 0.000137 and alpha was 0.05. And so the answer is yes also here. Again, that leads to rejection of the null hypothesis. Reject the null hypothesis. Step number 6 is our conclusion, which says at the 5% level of significance, this data does not provide significant evidence to conclude that the proportion of Americans who do not trust the media has changed from the 46% from 2007. So here it is in writing. At the 5% level of significance, this data does provide significant evidence to conclude that the proportion of Americans who do not trust the media has changed from the 46% from 2007. Here's another way to reject the null hypothesis or not when you have a two-tailed test, and that is using confidence intervals. So what you need to do is compare the confidence interval for P using the sample data, and if the confidence interval contains the null hypothesis, do not reject the null hypothesis. If the confidence interval lands away from the null, H naught, the null hypothesis, then the data contradicts the data contradicts the null hypothesis. Data contradicts the null hypothesis, and we reject the null hypothesis. So that only works for two-tailed tests. So if we go back to the previous example about the adults nationwide, whether or not they trust the media, if we compute a 95% confidence interval for the true proportion, and with the null hypothesis p equals 0.46, the confidence interval is 0.489, the decimal 0.489, comma 0.551, 0.551. And since it does not include the proportion, the population proportion 0.46 p naught, we reject the null hypothesis. So reject the null hypothesis. This concludes section 8.3.